All right, if you've ever watched the news, then guaranteed you've heard a weatherman at one point say high pressure or low pressure. And yesterday I had somebody ask me, what does that even mean? But I realized as I was trying to explain it, the concept high pressure and low pressure doesn't really make sense unless you understand the underlying fundamentals, which are air pressure and air density. And there's actually pretty easy ways to understand these two concepts. So even though it sounds kind of intimidating and sciencey, it often boils down to things as easy as like a stack of books or like people in a party. Those are two of my favorite metaphors that I'll explain in a minute. But first thing we have to do is just think about this little plot I have right here. So we have pressure and density on the bottom, or the x-axis, and then altitude on the y-axis. So our pressure is going to start very high, and it is going to rapidly decrease, and then it's going to decrease more gradually as we get higher up in altitude. Now, the exact same thing is true for our density, and it's going to almost, oops, that was a little squiggly. It's almost going to follow the exact same curve as our pressure. So, main thing I want to illustrate there is that pressure and density decrease with height, and their curves are basically the exact same, so it seems like pressure and density are very related to each other. So to actually understand what's going on here, we have to go in and look at air pressure. So let's come right here and add a new group. And let's use a nice red pen. We'll stick with air pressure first. So here's our world, and you know the atmosphere is around our world. Gravity is holding these air molecules and the particles that we breathe and what you feel when the wind is hitting you. Gravity is holding those close to the earth. So just looking at what's going on here, we're going to think about a column of air. So I'm going to try to draw a nice 3D column as best I can. Okay, so this is our column, and let's pretend it's 1 inch by 1 inch by 1 inch. Now let's use white for our air molecules. Actually, we'll use blue because that kind of reminds us of what the sky looks like, and that's due to scattering. I've done a different video on that. So close to the surface here, so we're imagining this air column starts at sea level and goes to the top of the atmosphere. Close to sea level, gravity is going to be stronger, so we are going to get lots of little air particles right on the bottom of this column. Now as you go up, these air particles are going to become a little more spaced out or less dense. That kind of gets into our density. And then eventually you're only going to have like 2 left. I should draw more on the bottom here to really drive this point home. So in other words, the density of those molecules is decreasing as you go up. But what pressure is the weight of all of those molecules, or the weight of the atmosphere above you. And while it doesn't seem like the air has any weight, if you were to actually add up all of the air molecules in this 1 inch by 1 inch by 1 inch cube going from sea level to the top of the atmosphere, it would actually weigh about 14.7 pounds. So what air pressure is really just the force of all of those air molecules pushing against you. So at all times, you might not realize it, but on average, you have about 14 pounds of air molecules pushing down against you. That's your air pressure. If there's more particles in this column, there's going to be more weight above you. So then your air pressure is going to be heavier. If there's less particles, there's going to be less molecules above you, and your air pressure is going to be less. Now this picture also kind of paints the idea better of that your air pressure decreases as you go up. The reason for that is if your air pressure is the weight of the molecules above you, if you're out on the surface, you have this entire column above you. If you are halfway up this column, now you only have like half of the column above you, but even less than that, you have just a fraction of the molecules left above you. My favorite way to think about this is if you're at the top of Mount Everest, you're actually above 70% of the air molecules in the atmosphere. And the air molecules become so few when you're that high up. That's why you need oxygen tanks. Down at just throwing out some random numbers, down at the surface, maybe we're breathing in 1,000 oxygen molecules. That's a completely made up number. But then up at Mount Everest, maybe you're only breathing in 300. That's not enough, so that's why you need an oxygen tank. Now, the other way to think about this, and I'll actually just start a new little page right here, is to think about, let's make it a nice drawing here, a desk. And on this desk, we have, we have a stack of books. So you have a stack of books right here, another book, and books like that. And those books are exerting a force against that table. Makes sense that if you have more books on one side, that force is going to get bigger. Well, it's the same thing with the molecules in the atmosphere. The more molecules are in your column, the more it's going to weigh, the more force it's going to push down against the surface, and that's your air pressure. So, yeah, just think of it as the weight of the atmosphere above you. Now, just want to click this back on for 1 second. If you think about what's going on here, this actually explains our air density as well. If you look down at the surface, the molecules look very dense. They're tightly packed. Whereas when you go up, there's maybe only a few left before you're just in space. So the ones at the top are going to be less dense. The ones at the bottom are going to be more dense. My favorite way to think about this, though, is actually people at a party. So, cancel. There we go. So if you have two houses here, and in these houses, you're throwing a party. So, in this first one, this is going to be close to the surface of the Earth. So this is where you have lots of air molecules packed in together. They're, for some reason, getting shorter. That is going to be a high density party. Now let's say, I don't know, it's getting towards the end of the night, everybody's going home, and you just have 2 people left. That's like the top of your atmosphere, and that is going to be low density. So this is like your surface, and this is like top of the atmosphere. And yeah, I probably didn't even need to go into that example. It is pretty intuitive. If you have any other questions, just let me know, and I'll maybe make another video to go further into this if we need to. But the main idea here is that air pressure and air density decrease as you go higher in the atmosphere. Air pressure is the weight of the atmosphere above you, and air density is how tightly those particles are packed together. Now, I will say one other thing, because you might be thinking, all right, who cares? So I'll just bring in one more example. And this is why air density is important. If you remember what we were saying about cold fronts, this is your cold air, and that is going to be dense. Now you have some warm air, moving in, your warm air is less dense. Oh. So when that warm air bumps into the cold air, it is going to lift up above it because it's less dense. It's kind of like your layers in like a salad dressing. The less dense layers go to the very top. And then the reason this ends up being important, it's actually one of the most important concepts in weather, is as air rises, it cools down. As it cools down, it can't hold as much water. As the water condenses, or the water vapor condenses into liquid droplets, that's where clouds form. And then that's where you get your severe weather right along your cold front right there. And let's even draw in little lightning bolts. All right, so that's air pressure, that's air density. Hopefully we laid a little foundation here, so next time we can actually dive into what high pressure and low pressure means and how that affects our weather. So thanks for watching.